Let's talk about momentum operator today. When you are studying quantum mechanics, and the first thing you need to know is how to use the operator to represent different physical quantities in quantum mechanics. Two of the basic quantities is the coordinate or the position of the particle and the momentum of the particle. Both of them should be represented by the operator. Okay, today I'm going to tell you how Dirac first derived a very simple and elegant form to define the momentum operator. The momentum operator can be written as in any textbook as P equal to, we use operator as a negative I H bar, and the first derivative, if you just pretend you see the one-dimensional form, it's just dir and dir x. So dir x just represent the first derivative in calculus. For example, the dir here, dir, if you apply dir x, it's called partial derivative. Apply to this to any function, then you get his first derivative. Okay, it's just a little bit of explanation of how to use this notation. Also, and in calculus, we know that we can use what we call the product rule to work out the product. If the function is written in the product form, we can use product rule. So based on this idea, we can also apply dir x to the product. In this case, we choose the coordinate multiply function. Okay. So these form a product. According to product rule, we can use that. First of all, we use the first derivative with respect to the x, then we simply get f. The second one, we got plus, this time we put x there, and what have left is dir x f. Okay. To emphasize that dir x is an operator, so I deliberately written this as a separate form. So this notation is slightly different from calculus, but in essence, they're the same. So if you arrange this product row, the result of product row, slightly, what we can have, can we just put the dir x? So we can put put the x first, okay? We can, from this here, we can obtain, from here, we can obtain that x dir x, okay? And minus, this is just like factorizing. So we got dir x, and this dir x and dir x, we just rearrange the result of the product row into this form, and then factorize that. We put f outside. So what have we obtained on the other hand? Then in this case, we got a negative f, right? Got a negative f. So this is a starting point where Dirac in history found out the generalized quantum condition. Let's go further. So we know that if we rewrite the result here, we got x dir x minus and dir x, the partial derivative, or you can just simply call the first derivative, and multiply x. So in this case, x and der x are considered as the operator, okay? And then we factorize f. So we got this very simple relation. And this relation exists since Newton invented calculus. But of course, nobody knew that this simple form can actually play the key role to unify the two early versions of quantum mechanics. One is Heisenberg's matrix mechanics. Another is Schrödinger's wave equation. At that time, before Dirac applied this simple relation, and these two early versions of quantum mechanics are not compatible. And therefore, there's a heated debate between Heisenberg's group and Schrödinger's supporters. Now let's go further. So if we multiply at this moment, so if we multiply negative I, let's say, we need negative, yes, we like negative, right? So if I multiply negative I, so we just multiply this factor, negative I, h bar, h bar. So h bar is just a different form of a Planck constant, namely h divided by 2 pi, as simple as that. So if apply these factors on both sides, then what we have, we got this simple relation. So we got, because it's because of numbers, so we're entitled to rearrange these numbers. In this case, I put this I h bar in front of the der x. And similarly, without changing the sign of negative sign, we just directly multiply these factors here. That is der x, okay? And what happened to the right-hand side? The right-hand side will simply became I h bar. Okay, I here, if you still haven't go to the detail of quantum mechanics, I is the unit of imaginary number. So that is -1, square root of -1. Aha, this is the haha moment. So actually, if we denote these factors as quantum of the momentum, then we got, so then if we denote this as momentum, can you see, which is consistent with the formula you saw in the textbook, then we got this the new what called commutativity or commutative relation for the two operator. So if I write down here, so from here we can get the x multiply the p and minus p multiply x will equal to I multiply the h bar. Of course, to emphasize these two variables are not just function, but the matrix, the operator, this operator. So we put the hat on each of them. So you can see that this is the key. That is how literally the Planck's constant is introduced in this computation relation. Now, in short, Dirac actually borrows idea from the classical analytical mechanics, namely the Hamiltonian mechanics or Poisson bracket. Then he simply written this short, he used this simplified note to represent this commutative relation in quantum mechanics. So equal to I h bar. So in this way, not only did Dirac to find the fundamental relation that to determine when and the quantum mechanics should be taken into account, should be applied, and it is criteria for people to choose between Newtonian mechanics and the new mechanics, namely the quantum mechanics. But also, he also found the consistent, a simple, consistent interpretation of why we should use this simple operator to describe the momentum operator in quantum mechanics. So this is a very brief introduction, but in history, it is by using this description that did Paul Dirac actually unify the quantum mechanics from, one is Heisenberg's matrix mechanics, another is Schrödinger's wave function. Okay, thank you.